来跳操。
嗯。
to make the
Hello? Can you guys hear me? All right. Hello, everybody. Welcome back to this lovely Monday. And today we are going to continue on our mining large graph lecture. All right, so your assignment 3 is due on Wednesday, and tomorrow is your wellness day. Enjoy your wellness day. What I want to say about assignment 3 is we are going to release your final project description. So you will have the chance to look at the description and see what you will need to do for your final project. So in general, well, your final project will be the same as your homework 3, but you will need to improve your recommendation system so that you can beat your TA's score. And in the end of the class, if you beat your TS score, you will be able to receive the full credit for your final project. If you are, well, based on your based on your prediction result, if you rank high in the class, we are going to give you pretty good bonus. I think we used to give people 3%, 2%, and 1% of the entire grade for your class. For example, if you're at the end, your weighted sum is 87, which might be a B plus. But if you're first one, if you rank the first in the final project, you have 3 points. So 3 plus 87, you have 90. That could make you A minus. Okay, so make sure you use this opportunity, not just to beat your TA, to rank high, but also to use all the knowledge you have learned in this class to build a really nice recommendation system that you will be proud of. Okay, so, all right, so today we're going to continue on this mining large graph. I have to say, this can be very confusing, this AGM model and how to derive it. So bear with me, pay attention. And if you have any questions, just ask me. All right, so remember we talk about different models, right? And let me go to this one. This is the easiest one. So remember, our goal is to be able to find overlapping communities in a large graph. So what we are saying here is, let's say we have a model. This is a model. The model has a few parameters. And we have some observations. Well, we have one observation. This is our graph. Our goal is to be able to use the observation, fit the model, or you can say use the model to fit the observation, doesn't really matter, to be able to derive the parameters of the model, okay? And this way we will be able to use the model to do all kinds of analytic stuff, and identifying community is one of them. So what are the steps required here? Well, first you have to look at the model parameters, right? So here your model has one parameter, which is P, very simple model. And what do you do after you have P? So first step, look at the parameters. Second step, look at your graph. So based on your graph, you look at the model, you look at the graph, you generate a target function, okay? So this is the likelihood function. So why do we call this a likelihood function? Because this is the likelihood of this model generating this graph. Okay, so to remember, to understand the process, this is important. The likelihood of this model to generate this graph. So based on this likelihood, now our goal becomes what would be the parameters, in this case P, that will give us the highest likelihood. So we want to maximize the likelihood. Maximizing this function. So the entire function is your likelihood. And we talk about one way to do this, right? So you can calculate the derivative and use the derivative to find the P, and you have this P. You plug in this P back to this function, you'll be able to generate the likelihood. And we say the likelihood in this case is still very small, although it's the maximum likelihood, because this model, sorry, this is just a parameter. This model is too simple. Okay. All right, so if you understand this, now you are ready for AGM. So last time we talked about this, so I'm just going to quickly go through this. Well, AGM is also a model. Remember last time, the simple model, we only have one parameter, P. And this time in AGM, we have all kinds of parameters. In this AGM model, we have parameter V, number of nodes. we have parameter C indicate the number of communities. We have the parameter M indicate the membership between nodes and the community. And this is binary. For example, this node is a part of community A and can be also a part of community B. Okay. Other than that, we also have this probability PC parameter, and this PC is each community C has this parameter. This parameter indicate the probability that two nodes, if they belong to the same community, the probability of there is a link between them. So think about this. Because a community by definition is a set of nodes with dense links, right? Densely connected nodes. So the probability should be high. And that's why we only define the probability of there is a link between two nodes if they belong to the same community. So this is by community, okay? All right, so with all these parameters, now when we see this network, what do we want to do? Remember step 1, step 2, step 3 is to take all these parameters based on the observation, formulate a likelihood function. Then we want to find the parameters that will be able to maximize this likelihood function. Cool. So think about this. What would be the variables in this likelihood function? Or what would be the parameters? Anybody? Remember in our previous example, your model has one parameter P and your likelihood function has what parameter? It only has P, right? What about this case? What would be the parameters?
4. E, C, M.
Okay, so Zun says M and V. Christina says V, C, N, and P. Okay, so Christina is correct, right? So every parameter is important. You have to have every parameters so that you will be able to generate this function. Okay, so someone is asking what is the, Bridget is asking what's the membership parameter. It doesn't really matter how we write it now, for now. This is just a variable that you have to set. So for example, let's say this likelihood function would have M, would have V, C, and M, P, C. A very simple example of this M could be just a matrix, right? And each column would be, sorry, each row would be a node, and 1, 2, and N. Each column would be a community, C1, C2, C3, and you have 1 and zeros indicating the membership. So Jin Chen said, it's like partition, how we make our communities, right? Well, I'm not sure I understand the question, but bear with me here. So everything here should be in the function. But remember what we were talking about. You take your parameter, you look at your network, and you generate this likelihood function. Okay, so let's put the likelihood function here. Right, so membership parameter is like the partition, how you assign partitions, how you assign nodes to communities in a partition. That's more accurate. All right, let's say this is our likelihood function. And we know that likelihood function, you're going to have some V and C and M and BC. And we say the way you generate the likelihood function is to look at all the parameters in your model, look at your observations, and generate this. So easy, right? You know how many nodes you have from here. So you can fix V. can you fix C? Or can you fix M? Can you fix PC? You can't, right? Because without any information, you only look at this graph, you do not know how many communities that you want to have. You do not know how many members, what's the membership look like, and what's the PC. So these are the parameters that you need to estimate. Okay, let's come back to our previous example. You only have P. You take P, you look at this, you can write this P function as the likelihood function, right? And this first term, this is the number of nodes, number of pairs of nodes that has a link. And this is the number of nodes that does not, numbers of pairs of nodes that do not have a link, right? Simple. But this looks complicated. So how do we do this? Jin-Chen said, here the probability P, we only consider each community. What's the probability for the link within overlapping community? Yeah, I haven't tell you that yet. I'm going to show you how to do this. All right, so we have the model. So now I'm going to show you how to write that likelihood function with C, V, M, and PC. So there is a given number of communities. So you need to assume some communities, a given number of individuals. So this is known. This is from your observation from the graph. And this is from your hypothesis. You can say I assume C equal to 3, but just bear with me here. It won't make sense. Each community can have any sets of individuals as members. So you have some membership. This is a membership parameter. Each community C has this probability PC associated with the community. This is the probability that two members of community C are connected because they are both members of C, right? We know this. If a pair of nodes is in 2 or more communities, then the probability of whether there is a link between them will be controlled by these 2 communities, right? So not just by one community PC anymore. So there's an edge between them if any of the communities of which both are members justify the edge according to rule number 3 here. So let's look at the next slide. Let's say your nodes are U and V, and you have an edge UV. Say UV are in communities C and D, but not other communities. Okay, so they both are in community C and community D. The probabilities that the 2 nodes in C are connected is PC, 2 nodes in D are connected is PD. This is just by definition. The probability of no edge between them is 1 minus PC times 1 minus PD, right? Independent. So no edge between them in community C. So this should be V. No edge between them based on the fact that they are both in the community D. So the probability of the link exist is the complementary of this probability. So it's 1 minus this. Okay, so pretty simple. We saw this before when we were working on your LSH. So let's say in general case, this case, we only have 2 communities. In a general case, if UV are members of a community set M, then the probability of an edge between U and V is the complementary probability of there is no edge between them. And this C is the one of the shared community between node U and V. Okay. And this is multiply. And we can do multiply because each community is independent. Are we good so far? So we know how to write this. Does this look familiar? Remember in our previous example, your model only has one parameter P, and this P indicates whether or not there is a link between any pair of nodes. Now we have a fancier way to write this probability based on all other parameters that we used in the model, right? So every pair will be different because they might share different membership. Before, if you take U and V, you got P. If you take K, node K and node J, the probability of there is a link between them is still P. But here you need to consider their shared communities. That's it. So how do we use this to write the target function or the likelihood function? All right, so we have this membership model. We want to take the model and generate a network. So this affiliation graph model generates the link based on the function on the previous slide. Okay, so which is here. For each pair of nodes in community A, we connect them with some probability of PA, right? This is by definition, but the overall H probability when you consider every community is this. Again, for two nodes, complementary probability of there is no link between them. There's no link between them. And how do you know there is no link? For each shared community, each community that both U and V belong to, you take 1 minus PC. And this C community is the intersection between the communities that contains U and the communities that contains V. Okay, pretty cool. Now this function already incorporated many things, right? It incorporated PC within the community, incorporated membership, also talk about how many communities you would have. All right, and if U and V, they do not share a community, we will just set a small constant value for this probability, because if they do not share any community, means the probability of there is a link between them should be very small. So we set it to a very tiny value. The epsilon is a very tiny number. All right, cool. So this is how we would be able to write the target function, but not quite yet. This is the way we can write the probability of there is a whether or not there is a link between any pair of nodes based on all the parameters we have. Then we're going to look at how we write the overall likelihood function. So basically, we are talking about from a model, we can generate a network, and based on all the parameters, these networks can be non-overlapping, can be overlapping, can be nested. So all kinds of networks can be expressed with AGM. But now we know how to write that probability function. Still, how do we detect communities with AGM? So to detect communities with AGM, we want to take a given graph, find the model parameters, like what we did to find the p-value in that simple example. And that model would have your affiliation graph M, number of communities, and parameters PC, which is very cool if we can find the parameters. I haven't tell you how to write that likelihood function yet. I haven't tell you how to derive all these parameters yet, but if we can do that, the membership graph and the number of communities automatically tell you how to partition the graph into all kinds of community settings, right? It can be overlapping, can be non-overlapping, can be hierarchical. So how do we do that? We're going to use maximum likelihood estimation again. All right, so let's look at maximum likelihood estimation with a very simple example again. So say you're given some data X, and your assumption, your model, is the data is generated by some model f theta. F is your model, theta is your model parameters, and our goal is to be able to estimate the probability of given model parameters to see your X, and we want this to be high, right? In our graph example, we say, all right, the model only have a parameter P, and we want to find this P value to have this to be high, right? Given the P value, we want to be able to see the network with a high probability. And this is the probability that our model with the parameter theta will generate the data. So let's find the most likely model, including the parameters. We are basically estimating the parameter because the model is fixed that could have generated the data. That means we want to find the maximum theta to maximize the entire likelihood function. All right, so let's say your data is a sequence of coin flips. So data X is 1 0 0 0 1 0 0 1. So coin flips 0 or 1. Your model will return 1 with some probability theta, else it will return 0, right? So very simple model. So what is your P X given theta? Assuming your coin flips are independent, this means we are going to first model individual instance in your data. What would be the probability of some parameter seeing 1? What would be the probability of some parameter seeing 0? 0, and so on. So this is your target likelihood function. Okay. And what is the probability of seeing 0, seeing 1 given some parameter? Well, theta, right? This is by definition because your f function returns 1 with probability theta. So then this target function becomes theta to the power of 3, 1 minus theta to the power of 5. This looks like our previous simple example of the graph, right? Some numbers there. So tell me, why do we have a 3 here? How do we know this is 3? Anybody?
Because there are 3 ones.
You have 3 ones here. Why do we have 5? Well, you have 5 zeros. Easy. Right, so remember what I said. First, look at your parameters. Second, look at your data. Third, from your data and your parameter, write your target function. Comes this. Cool. So our goal is to be able to find the theta that will be able to maximize this probability. So how do we do that? Well, we take the derivative, we find, we set that function to 0 and find a theta number, plug it back, and we'll be able to find the theta that will be able to maximize the entire function. So here we can see that, okay, so this function is here. And you can see here you have first derivative equal to 0, and this is when your theta equal to 3/8. This tells you that when your theta is 3/8, you are going to have the maximum likelihood of generating this sequence. Well, what does it mean then? Well, this means this coin returns 1 with the probability less than 50%. Returns 0 with a probability higher than 50%. Is this correct? Shouldn't it be 50% either way? Well, 50% both way, 1 and 0s. Why does this happen? Why do we have 3/8? Well, because this is what your data tell you, right? If you're going to have a 50% or 0.5 as your theta, you're going to have equal amount of 1s and 0s. But your data tells you that you have only 3 1s, but you have 5 0s. So most likely your coin prefer 0 than 1, right? So the probability, the parameter that would have the highest likelihood of the target function is what? 3/8. This is maximum likelihood. Exactly the same as what we did on your graph with a simple parameter p. All right, so how do we use this for AGM to estimate the parameters? For AGM, say we want to use AGM for modeling the graph below here. And every time when you see many parameters in a model, we have to preset some of the parameters. If we don't, there is no way we will be able to solve it because there's too many combinations. Say, let's preset the parameters. Say we assume there are 2 communities. The communities are C and D, and the probability of 2 nodes within C has a link SBC. The probability of 2 nodes in D has a link SBD. Okay, so parameter, community parameter has been set to 2. We haven't set this yet. We also determine the membership parameter or use some temporary hypothesis. Every time when you see people say temporary hypothesis, that usually means they take a small sample of their data and use brute force method or some naive method or like normalized cut to figure out the partition because it can work on small data set. All right, so say we have determined this hypothesis and determine the community membership. We say community C has XYZ, community D has WYZ. Okay, X, Y, W, WYZ. All right, 2 communities, awesome. So what are the things that we still need to estimate? Remember, we have the model has n number of nodes. This is good. 1, 2, 3, 4. The model has C. We know C equal to 2. The model has membership. We set it to this. So I put a star, means this is our hypothesis. And we also have PC and PD. This is something that we want to estimate. Okay, so cool. We can actually start to estimate this, but how? Remember, I said 3 steps in writing a likelihood function, right? First step, look at your parameter. Second step, look at your data. Third step, take your parameter and take your data, write this function. So how do we write the function? Here. So again, your observation, your graph, plus your hypothesis that set your C and M parameters. And remember, we derived this, the probability of there is a link between node U and V is 1 minus the multiplication of all the communities that has membership U and V1 minus P C. Right? This is how we can formulate the probability of there is a link between any pair of nodes in the graph. All right, so let's look at every pairs of nodes here. Say, let's start from X and Y. So PXY, let's look at PW and X. So PW and X, do they belong to the same community? Well, W and X are in community C. Cool, so the probability of there is a link between them is PC. Remembering our simple model, we don't really need to look at this, right? We will just say, all right, this is P. For every pairs of nodes, this is P. But for now, we have AGM and we have membership setting. We have this fancy way to derive the probability, so let's use it. 1 minus 1 minus PC equal to PC. The probability of there is a link between X and Y. Let's look at X and Y. Are they in any community? All right, X and Y are in C. Awesome. Y and Z are in D, so PD. W and Z are in D, so PD. All right, so how many links do we have to do this? You have 1, 2, 3, 4 nodes. You have to do this for every pair. I remember in our previous example, in this P example, it's C15, choose 2, it's 1, 0, 5. In this case, how many pairs we have? What's 4, choose 2? 6. All right, so we have done 1, 2, 3, 4, 2 more to go. W and Y, are they in the same group? W and Y, oh cool, they are in C and in D. Finally, we can use our target function. So it's 1 minus PC times 1 minus PD, right? Because they are in 2 communities and the probability, this part is the probability that there is no link between them. What about XZ? If you look at X and Z, there's no link between them. I remember always look at the third step of writing your function, likelihood function. You need to look at your observation. So X and Z, there's no link, so it's a tiny value. All right, so we decide on this. Great. What else? What else do we have to do? Remember in our last example, very simple one, you already know P. Then what do? You look at your graph, and if 2 nodes has a link, you say P times P. If you have 2 nodes that do not have a link, you just times 1 minus P. Right? And you do exactly the same here. So you take this, you start from W and X. W and X has a link, so we put it here. Independent, marginalized probability, so you just multiply them. W and Y has a link. Okay, so okay, just use the probability you derived. X and Y has a link. You can just use it. Y and Z has a link. You use it. W and Z, they do not have a link. All right, so what is the probability of there's a link between W and Z? Okay, here, PD. So this should be 1 minus this. XZ, you do not have a link, so it's 1 minus X. Okay. Then you look at all the things you just calculated, you plug it in. What's XY? What is the probability of there's a link between the W and X? PC. This is PC. How about the second one? WY. Oh, this is a much larger term. what is XY, PC, YZ, YZ, PD, 1 minus WZ, WZ is PD, and what's this? A tiny value. So, okay, cool. So you rewrote the entire thing into a target function that only contains variables from your model parameters, PC and PD. Right? Remember we say N is set, excuse me. Number of communities set, membership is set, right? This is from hypothesis, only PC and PD we don't know. But now it's very cool. You can write this likelihood function and your goal is to maximize this likelihood by finding the right PC. So how do we do this? Again, our best friend, calculus. So we want to find the values of PC and PD that will be able to maximize this. The lags factor can be dropped. This is constant, it's not important. We want PC to be as large as possible. All right, so I'm going to tell you here, it's just some simple way to estimate it, but you can take this function and find partial derivatives and find the PC and PD that will be able to provide a maximum value for the function. But let's just look at the description here. We know that PC should be as large as possible because you have a PC square here, but you have some PC here. Given PC equal to 1, because PC is the probability, is a probability value, the maximum value will be 1. If PC is set to 1, your PD, the entire function becomes this, your PD will be equal to 0.5, then this is when the expression has the maximum. This means the maximum likelihood for the graph on your last slides can occur when the members of C are certainly to have an edge between them, and there is a chance that 50% chance that the joint membership in D will cause an edge between the members. What does it mean? This means if you set PC to 1, your PD to 0.5, this will give you a probability value. And this probability value will be the maximum likelihood given that community equal to 2, membership is from what you have set. And the node, number of nodes you already know. This will be the likelihood. And if the likelihood is very high, we will say, okay, cool. We found our communities. The community is 2. The number of communities is 2. And we also know the membership. We know how to cut the graph to fit that membership. But in practice, this is not going to happen. You can calculate PC and PD to have the highest likelihood, but you still do not know if this is the highest one. For example, well, you do not know if this is the highest likelihood. If you change the community to 3, or you keep the community to 2, but you change the membership, right? If you do this, if you set the community to 3 and you have a new membership, how do you estimate the likelihood? Well, you just do the entire process all over again to generate this and find PC and PD. And in this case, you have 3 communities, so it can be it's PC, PD, and PE that will maximize this likelihood function, right? Then you plug in the number again, you generate the likelihood function. Then you compare this number from your previous number to say which one has the highest likelihood. If this one has the higher likelihood, you will say, all right, this setting is better than the previous setting. Okay, and then you keep changing. You continue to change your C, change your M to see if you will be able to find one setting that have the highest likelihood among all different settings. So before we take a break, one thing that's very important, just to make sure you're not confused. In this case, the maximum likelihood estimation is done by setting some parameters, in this case C and M, note, and estimate the probability. And the maximum likelihood is estimating these probabilities so that this setting can have the maximum likelihood. Let's call this maximum likelihood 1. Okay, but we're not done yet. You're going to do another setting. You say, all right, so now let's do C1, assuming C1 equal to 3, this is C0, M0, and M1, a totally different setting, and your N is the same, right? Number of nodes are the same. So based on this setting, you can also write a target function for your likelihood. Then you use the same way to maximize the likelihood. You plug it in, you plug that number back to generate the likelihood. You have the maximum likelihood for the second setting. Okay, then you compare this to, you say, okay, so this one is maybe 0.2, this one is 0.3. That means this is not good. We're going to stick to this one, but we are not finished yet. We can still change the parameters and do the maximum likelihood again and again and compare the likelihood. And you can easily see that this is not the best way to do it because it's very time consuming and you don't know how to change the parameters to give you the best community setting, right? You don't know based on this 0.2 and maybe, sorry, let's do this 0.3, 0.2 here. You only know that this is better than this one, but you don't know how to make this one better, right? Do I need to have more communities? Do I need to change membership? You don't know. So how do we deal with this? When we come back, we're going to look at AGM in more details, and then we are going to talk about the method that will be able to help us to quickly find your C, M, and probability. All right, let's take a 10 minutes break, come back at 7. If you have any questions, leave it in the comment. I will answer them when I come back.
这样的那个黑金是目前已经卖完了，就是已经没货了。然后金棕银扣的话还有2个，这个2.55这个价格基本上也是到底了，再谈也谈不了几百块钱的，因为确实我这个东西国内现货的话，二手店老板是跟我回收的2.55。
All right, I'm back. Let's continue working on our AGM. Do we have everyone back? Can you guys hear me? All right. All right, AGM, we were here. Okay. So how do we do MLE for graphs? Based on what I have already told you, let's look at how we do this again. So your model would generate a probabilistic adjacency matrix like this. What does it mean? Well, remember in your target function, you are going, in our previous example, you are going to estimate this PC and PD, right? And for every link, for every possible link in the graph, you can write the probability of there is a link between them using PC and PD. How do we do that? Here. Right, every link you can write it with PC and PD. And based on your MLE, you already estimate PC and PD. Okay, so you can write this and you can generate this adjacency matrix. This adjacency matrix is fairly simple. Every cell is the probability of there is a link between two nodes, right? And it's always 0 because in our case, we don't have a link like this, right? We do not consider this the case. So you take this adjacency matrix with all the probability you calculated, and you want to generate this graph, and that's your maximum likelihood you just estimated, right? So in other words, that maximum likelihood is the probability that this adjacency matrix will be able to generate this observation. This observation is based on your real graph. So given a graph and your parameter, we calculate the likelihood that your parameter will be able to generate this graph. And this is the probability of graph given parameter, right? Graph, parameters, you estimate them, you have this probability, adjacency matrix, you can generate this likelihood function, and which is this. Right, so still remember this? You take your observation, you say for every pair of nodes that has a link, this is the probability. For every pairs of nodes that do not have a link, this is a probability. So our goal is to find this parameter set V, C, M, and PC such that we will be able to say, we take the AGM, we generate some parameters and likelihood function based on the observation. And we have the observation, so we can say, given the observation, given the likelihood, this P function will be able to generate the graph with a high likelihood. Okay, cool. So how do we find this set of parameters that would be able to maximize the likelihood? Again, this is different than MLE. In an MLE, we already know V, we already set C, we already set M. We are only looking at PC as two unknown variables in our previous example, and we use MLE to estimate this, right? This is only one likelihood, ML1, that we estimate. But we still need to be able to vary the C, vary the M to be able to generate multiple MLs and find the one with the highest one. So that's here, maximize the likelihood. So how do we do that? Well, our goal is to be able to find all these parameters such that we can maximize everything here. The problem is that finding this B means finding the bipartite affiliation network like this, because this is our previous setting, and there's no nice way to do it, meaning it's very computational, expensive, especially for large graph. You might not be able to find the best solution. So fitting this entire function is too difficult. So we are going to change the model, make it easier to fit. So until now, what you have learned, the takeaway is you can have a model, you can design a model, and that model would be able to be the model is very expressive. The model can explain many different types of community settings in the graph. Then you take the model, you fix some parameters, right? In our example, if you fix some parameters, then you can use the remaining parameters in your graph to generate a target function. You use maximum likelihood estimate to estimate this unknown parameters to maximize this likelihood. Then you have to look at your fixed parameters. You have to vary them, generate the maximum likelihood estimate again, and compare this with the last iteration to see which one's better, right? And you can see that between each iteration, every time when you change your fixed parameters, there is no good way to say, all right, the last one gives us a better result, so this is the direction we should go. We should increase C, or we should increase membership for certain nodes. We don't know, right? There's no good direction to do it. So what we want to do is we want to relax this model so that first it still be very expressive. It needs to be able to still describe various types of community settings. Second, the target function or the likelihood function needs to be something that we can find the optimal solution very easily, okay? So that's why we have to change the model like this. So this approach is called the big clamp. And it's a relaxation of AGM. In this case, we are saying memberships have strength. So in this case, well, in the AGM, your membership can only be 1 or 0, right? You either belong to a node, either belongs to a community, or it doesn't. If you look at here, our new goal, or our new model says, instead of having 1 and 0, let's use a strength. So FUA means the membership strength of node U to community A. And this FUA should be larger than 0. If it's 0, means no membership. And the larger the FUA is, the stronger the membership is. Each community A links node independently. And we define that the probability of U and V, they both in community A, to have a link between them is this. Okay, so remember in AGM, this is just defined as PA, right? But now we want to express this with a membership. So 1 minus e to the power of minus FUA times FEM. Okay, how do I know the definition is correct? How do I know this makes sense? Well, let's look at some examples. This is a probability of there is a link between U and V given that they are in community A, right? This is our definition. Say if U and V are not in the same community, one of this will be 0, right? Because FUA is 0, meaning U is not in community A, and VA is 0, means V is not in community A. So if this is 0, 1 minus e to the power of 0 is 0, right? 1 minus 1 is 0. Oh, okay, awesome. Good. Do we want this? Well, yeah, because they are not in the same community, so the probability of there is a link between them should be 0 or a small number. If U and V are both large numbers, that means they have strong membership to community A. Then we want this probability to be large, right? Because they are in the same, they are highly likely to be in the same community A. So if these two numbers are large, e to the power of minus a large number will be 1 minus a small number. So this will be a large number, right? So great. This P is large if both of them are large. If FUA and FVA are both small numbers, the probability based on our definition here is 1 minus e to the minus of a small number, right? Because these two are both small numbers, and this becomes 1 minus a large number, and the result is a small probability. Awesome, right? They both small, so we want to have a small number. So this makes sense. Let's look at how we use this to, how we can use this to find the parameters. All right, so this is our definition. The probability of connections of or links is proportional to the product of the strength. If one node doesn't belong to the community and you have a 0, then this PUV would equal to 0, right? We already know this. The probability that at least one common community C links the node is this. The same thing as before, right? So the probability of there is a link between PUV is 1 minus all the communities. Now we consider all the community because we do not know if you actually belong to a community or not. We only know the membership strength. So we want to take each community, calculate this. This is the probability that there is no link between U and V based on this community C. And we just multiply this probability by the same way to calculate the probability from other communities, right? So this is all communities. So to better write this, we can do this. If you look at this table is the community strength. The number of rows are the number of nodes, and the columns are the number of communities. So in this new approach, the big claim, you still need to preset the number of communities which is generally okay because you might already have a target number of communities that you want. What you don't know is which node belongs to which community. Okay, so you create this matrix. You have community, you have nodes, and each row is the membership strength. You have to initialize this matrix by taking a small sample, or you take one node, you look around this node and do a very simple calculation. You say, all right, based on my neighbors, I think I have a very strong membership to A, less strong to B, and so on. So some guess, good guess. Okay, it's in the paper if you are interested, but you just need to know that you initiate this table by setting the community and by setting each membership, by setting the membership for each node by looking at the node's neighborhood. So once you have this, community A links node UV independently. So PAUV is this, right? We know this by definition. The probability that at least one common C link them, the probability between, the probability of there's a link between UV is this. And we can easily write this as a dot product like this. So this is your matrix. This is your node U, node F, and node W. FU times FV transpose, well, because they are all the same dimension, so you want to do transpose, but this is just dot product. So 0.16 UV, 0 times 0, 0, 0, 0, and 0.2 times 0.8, you have 0.16. Okay. So the probability of there is a link between U and V is 1 minus 0 minus 0. 0.16, 0.14. So pretty cool, right? You just do a dot product and you already considered all the communities. And you can generate this probability value. And you can do also UW and VW. Let's look at UW, 0, 0, 0, and 1.2, 1.8, 0.88. VW is 0, 0, 0, 0, 0, so 0. All right, so now you know how to write this. The next question is, now we still want to maximize this, right? Our old friend is just, in this case, BigClam. We can rewrite this in a different way in our new settings. So in this case, we want to be able to maximize this with regards to our new definition of the probability matrix. And we are going to talk about this next time because it's your quiz time. All right, any questions? All right, we can start your quiz. Please turn on your camera. You have until 8 p.m. today. This is very important. You have until 8 p.m. You have until 8 p.m. You have until 8 p.m. to finish your quiz. Please turn on your camera for your quiz, and you can find your quiz on the Blackboard. We still have a couple people who do not turn on their camera. Please turn on your camera.
Hi, time is up, so you can upload your solutions on Blackboard, and my office hours starts at 8. Thank you.